This show is all about water ice, from how some got to the moon from Earth to the discovery of exocomets.
And how we found DNA and RNA bits in meteorites.
Plus, we take a look at how our solar system formed.
And that one telescope finally passes all of its alignment steps.
Later in the show, Beth will be joining us for a review of Netflix's The Atom Project.
All of this and more is coming at you right here on The Daily Space. I'm your host, Dr. Pamela Gay.
And I'm your host, Eric Mattis.
And we're here to put science in your brain.
The JWST finally completed its 7th and final alignment phase, confirming that all 4 instruments are aligned and focused on the telescope, allowing it to produce diffraction-limited images. The diffraction limit means that the resolution is as good as it can get for a telescope of that aperture. Each of the instruments receives light from the telescope at the same time, allowing for simultaneous operations. According to the scientists, the telescope is now performing even better than expected. The next step, and the last step before producing science, is science instrument commissioning. This step is the conclusion of a quarter-century of work for some scientists, such as wavefront sensing and controls scientist Scott Acton, who said, "These images have profoundly changed the way I see the universe. We are surrounded by a symphony of creation. There are galaxies everywhere. It is my hope that everyone in the world can see them."
This is another story where I again have to stipulate that I'm not a biologist. So apologies if we trip over that aspect of the science at some point. In a new paper published in Nature Communications and led by Ashari Abba, scientists have revealed that the last 2 informational units of life's building blocks, DNA and RNA, have finally been found in meteorites. This means that all 5 of those units have now been discovered in rocks that came from space. The 5 components are nucleobases, which belong to classes of organic molecules and have pretty big variety. And the last 2 bases, cytosine and thymine, the C and T of DNA pairs, took this long to find because of their more delicate structures. Those structures may have degraded using previous sampling techniques, which I have to admit is kind of cool. And here I quote the press release. In the earlier experiments, scientists created something of a meteorite tea, placing grains of meteorite in a hot bath to let the molecules on the sample extract into the solution, and then analyze the molecular makeup of the extraterrestrial broth. End quote. The newer sampling technique used cool water extraction instead of hot formic acid, preventing the destruction of the more delicate molecules. And the instrumentation has improved, becoming more sensitive and able to find smaller amounts of molecules. Now, none of this means there is life on asteroids, and it doesn't prove that asteroid impacts seeded life on Earth somehow. It does give scientists more molecules to use in lab experiments designed to understand just how life came about here on Earth. Co-author Jason Dworkin sums the work up thusly. This is adding more and more pieces. Meteorites have been found to have sugars and bases now. It's exciting to see progress in the making of the fundamental molecules of biology from space. End quote. And maybe they can use this new technique on those samples due back from Bennu. While space rocks are great for gathering all kinds of data about our solar system, they are also rather difficult to get your hands on. Sure, tons of space matter enters our atmosphere every day, but most of it burns up before it hits the ground. And if it doesn't burn up, there's a high probability that any surviving meteorites landed in the water, or someplace equally difficult to get to. This is why scientists rely heavily on Earth analogs for research. If we can understand how biology or geology works here on Earth, we can apply that to other worlds, at least in terms of possibilities and maybe probabilities. Researchers recently analyzed rocks from the Persian Gulf near Oman in an effort to understand just where microorganisms called methanogens could exist. Their results were published in the journal JGR Biosciences with lead author Alto Hals, who examined rocks called ophelites. These are rocks that once were part of an ancient seafloor and at some point reacted with water to produce hydrogen gas. The process is called serpentization, and that gas can be used by microorganisms for energy. The team wanted to find out what effect this process and those rocks could have on the biodiversity of any ecosystem hosted within. Why? Well, as Howells explains, it is believed that processes like serpentization may exist throughout the universe, and evidence has been found that it may occur on Jupiter's moon, Europa, and Saturn's moon, Enceladus. End quote. Those icy worlds are key targets in the search for life beyond Earth. Unfortunately, they discovered that not all of the ophelite ecosystems could support methanogens, but that's okay. Those rocks could host sulfate-consuming organisms instead. And the research also suggested that methanogens require more energy in these types of rocks, as opposed to freshwater or marine sediments, possibly due to high pH levels. It's always good to add ideas to our toolbox when it comes to searching for life beyond Earth. Hal notes, quote, "If we can develop simple models with energy supply as a parameter to predict the occurrence and activity of life on Earth, we can deploy those models in the study of other ocean worlds." End quote. Next up, we'll look at how water on Earth may have become water on the moon. Stay tuned.
Science has long known that there is ice on the moon, and new research in the journal Scientific Reports shows where some of it came from: the Earth's atmosphere. Now, most of the moon's ice came from the same source as that of the Earth, comets and asteroids impacting on its surface. According to the study, a minimum of 1% of the Earth's atmosphere has escaped and been deposited on the moon. This works out to 3,500 cubic kilometers of ice. So how did all of this ice get from the Earth to the moon? It's a little complicated. Hydrogen and oxygen ions, molecules with a net electrical charge, escape the atmosphere and follow broken magnetic field lines straight away from the sun. These field lines often reconnect to form a closed loop around the Earth again. At some point in the return portion of this thousands of kilometer long journey, these hydrogen and oxygen ions smack into the moon, which passes through the Earth's magnetotail for 5 days of its orbit. The material forms permafrost in the shadow portions of the lunar north and south pole, and has since the end of the late heavy bombardment. First author Gunter Klatechka said, quote, "It's like the moon is the shower, a shower of water ions coming back to Earth, falling on the moon's surface."
One of the old favorites for folks looking to understand solar system formations is the star Beta Pictoris. This young star was discovered to have a disk of material around it in the late 1980s. And as our technology progressed, we found more and more cool stuff in this 20-million-year-old planetary system. In recent years, 2 gas giants were discovered in the system. And now, thanks to data from the TESS mission, individual comets have been seen as well. I have to admit, I didn't think we were quite to the point of making this kind of measurement, but last night I read the paper in Scientific Reports, which was led by Alain Le Cavalier des Étongs, and I'm a believer. Beta Pictoris is an edge-on system just over 60 light years away, and the combination of a large central star and perfect alignment allows us to catch objects passing between us and the star with relative ease, including, just barely, the passage of comets. In 156 days of observations with TESS, 30 different light dips were detected that are consistent with the passage of comets in front of this hot A-type star. The depth and length of each dip in the light, presumably caused by these comets circling Beta Pictoris, allowed rough sizes to be calculated. Remarkably, the scatter in sizes observed in Beta Pictoris comets is statistically similar to the distribution in our own solar system. This seems to reflect comets forming in the same way in that system as they formed in our system. Now, for those of you asking, but how do they know they are comets and not something else? Well, I'm with you. Star spots and other misbehaviors in stars can masquerade as transits. To prove something is a comet, you really want to be watching the star with a spectroscope so that the gases in the star can be measured as they are backlit by the star. And while all 30 presumed comets weren't watched this way, there have been spectroscopic measurements of comet transits in the past. Here, past behavior is used to inform current interpretations. And the size distribution really makes sense for the answer being comets. This paper could be proven wrong, but I think they're right. And until we get even better systems in space, better spectroscopic systems in space, this is the data we have. And this discovery is kind of awesome. As good as we are at getting to see young solar systems, there is so much we still don't understand. One of our greatest frustrations is our inability to fully understand how our own solar system formed, coupled with our inability to resolve solar systems like ours orbiting distant stars. This system, with 4 small rocky worlds near the Sun and 4, possibly 5 gas giants, is so far unlike anything else we've ever seen. The distributions of objects we see, along with their chemistries and crater histories, can, however, largely be explained by the 2005 NICE model, which was developed by a large collaboration of researchers who met in Nice, France. It states, to radically oversimplify, that the gas giants started out in positions much, much closer to the Sun. And after some sort of unnamed instability occurred, the gravitational effects of Saturn and Jupiter were a driving force in flinging Uranus and Neptune into the outer solar system. This model works best if a 5th gas giant is added. But the model predicts that the 5th gas giant, or 9th planet, would have been radically flung out of our solar system. But the model isn't perfect. The timeline for when all of this moving around took place puts the planet flinging hundreds of millions of years after the gas disk of our early solar system would have been dissipated by the sun's heat. This is both inconsistent with the chemistry of moon rocks and what we are seeing in other solar systems. Enter Bebe Liu, Sean Raymond, and Seth Jacobson. In a new paper in Nature, these 3 scientists present detailed models that ask, could the sun's destruction of the gas left over in the early solar system have been the instability that caused the solar system's rearrangement? This one change moves the rearranging of the solar system to the first tens of millions of years and makes what we see here consistent with other systems. That is excellent. It also has an interesting change involving a possible 5th gas giant. In the NICE model, and here I quote a release from Michigan State University, that extra planet was hammer thrown from our solar system during the instability. End quote. If that's true, Michael Brown's 9th possible planet isn't out there, unless it was stolen from another solar system. In this revised model, the potential extra planet is not required in the same way, but also isn't flung away in the same way. So, more work is needed, more observations are needed, and hopefully, we're within a couple of years of knowing if our solar system has one more gas giant, and being able to use that information to revise our understanding of the solar system. Next up, Eric is back with a surprise Chinese launch And Beth brings us a review of one of the most heartwarming sci-fi movies so far this year.
On April 29th at 4:11 UTC, Long March 2C launched the CV-1 and 2 satellites into orbit from the Xiaotian Satellite Launch Center in China. These two satellites are optical imaging satellites with a 50 centimeter per pixel resolution and were launched for a subsidiary of state aerospace company CASC. And now for that review.
Before I get into my actual review, I would like to thank the two people that told me I should watch this movie, both of whom are my bosses. Being a mom is sometimes not an easy gig, and they both heard my frustration and concern that I am, well, not a good mom. They then separately recommended I watch The Atom Project, and since it stars Ryan Reynolds, I didn't really find that a challenge. And it did help, so thank you, Pamela and Rebecca. On to the movie. The Atom Project is a science fiction time travel movie where the title character Adam goes back in time. The film opens with a space battle. Adam, it seems, has stolen his jet, and the people he stole it from want it back. He's shot in the ensuing dogfight, but he manages to punch a wormhole through space-time and get through it before his ship is blown up. Next up, we meet the younger Adam. He's about to get his butt handed to him by a bully. But he cannot help himself and keeps making sarcastic remarks at the bully and his friend. This doesn't help his situation any, and here we see that younger Adam is a geeky, smart, asthmatic, and not physically inclined 12-year-old kid. It's not easy to see the older version in the younger, and that right off is intriguing. Obviously, older Adam runs into younger Adam at home later on, and it doesn't take long for the younger one to figure out that they are the same person. There is a lot of sniping and poking at each other, which is kind of endearing and funny. It's also kind of how I expect any of Ryan Reynolds' children to turn out, to be honest. Behind all of that delightful banter, time-traveling Adam is dealing with his bullet wound and navigating just how much to explain to his younger self. This is where the science fiction plot comes into play. Adam is trying to rescue someone from a nefarious plot to control the future. And from there it would get spoilery. So now let's talk about what I liked and why, as well as some of that science stuff. First off, the movie is funny in a charming way, as I would expect from a Ryan Reynolds, Sean Levy movie. This is the same duo that brought us Free Guy, after all. Second, the script hits a lot of great notes, finding emotional moments in what could have just been a popcorn movie, full of great action sequences and no heart. The action sequences, though, are really good. But in the midst of all that is a story about grief and family and love. It's really lovely. So, why did my two bosses recommend to me in the midst of my parental breakdown? There is this one really touching scene between older Adam and his mom, played by Jennifer Garner, where he seeks to reassure her about how good a mother she is and that her kid loves her. She doesn't know who this person is that's being nice to her over a bar in a pub, but Garner does a great job of letting the fear and wonder and gratitude played over her face. I needed that moment. As for the science in this movie, there's actually quite a bit of it. Of course, time travel is the main topic, and I'm not going to get into that too much, although I did like the way they handled things like causation and paradoxes. But the part that really hit home was a graduate physics teacher talking in their lecture about how these are the problems their children will solve, and the way the students were reacting about the impossibility of even making it that far. Physics, as I know all too well, is not easy. Also, they touch on the phrase, "it's later than you think," referring to how there is never enough time to do all the things in your life, so do them sooner rather than later. I liked how that tied nicely into the time travel theme as well. So, overall, a bit of science, a lot of action, but most importantly, a ton of heart makes The Atom Project a delightful movie. It was produced by and is available on Netflix, if any of you are still subscribed to that particular service. Please note that we received no compensation for this review. This has been the Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we share thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.